In the previous 4 videos, we walked through the proofs of our 6 rules for taking derivatives of rational functions. Now, I'm going to reference them in their differential form, and I would highly recommend that when working with derivatives, you first start with the differentials. It will help with your understanding of the chain rule as it comes up. It'll help with your understanding of implicit differentiation. So just to form good habits, I highly recommend that you pattern your method for taking derivatives after what I do here. So these are our 6 rules. We have our constant rule that the derivative of any constant is 0. We have that if we take the derivative of a constant or the differential of a constant times a function, that constant can factor out. We have that the derivative of the sum or difference of 2 functions is the sum and the difference of their differentials. So in this case, you can think that the differential distributes across addition and subtraction. So just picture this d, the way it behaves with addition is the same way multiplication normally works. It distributes. Now, multiplication, the differential does not distribute across multiplication directly. What we get is that we get v times the differential of u plus u times the differential of v. And then similarly, we have a quotient rule that we do the derivative of the bottom times the derivative of the top minus the top times the derivative of the bottom over v squared. Sometimes people think if you think of the top as high and the bottom as low, that this, so a mnemonic for this is it's low d high minus high d low all over low squared. Some people use that as a mnemonic. And then finally, our rule for taking powers is that the exponent up here comes down and becomes our coefficient. The power reduces by 1, and of course we still have the differential of u. Do not forget when you're using this differential form that you've got to always write du or du dv. If you drop those, then when you go back to take derivatives, you'll have pieces missing. So with that said, let's jump into our first example. We'll take the derivative of a basic polynomial. So let's say that f of x is equal to, let's say, 3x squared plus 5x minus 4. And we want to know what is the derivative. What is f prime equal to? So, as I said, I'm going to approach this always thinking of this as differentials. So I first compute the differential of 3x squared minus or plus 5x minus 4. And when I look at any expression, I'll look at how is this algebraic structure, how is it pieced together? What are my building blocks? And I can see I've got a lot going on, right? I've got multiplication, I've got exponents, I've got addition. But the very first thing, the outer combining factors here is addition and subtraction. So using my sum and difference rule, I know that the differential will distribute right across addition and subtraction, which means I can rewrite this expression as the differential of 3x squared plus the differential of 5x minus the differential of 4. Right? So I've just distributed across using my sum and difference rule, which I said we can imagine this as the differential distributes across addition and subtraction. So now we've got to compute these separate differentials. So here, I'm going to go very slow in this preliminary example. As we get more examples under our belt, I'll be faster. But here, am going to use the constant rule, right? The derivative factors or distributes or moves, however you want to think it, right past constants. So that's going to go right there. Same here, that'll go right past the 5. And then we know that the differential of a constant itself is 0. So using those 3 ideas, or 2, however you want to count it, this is 3 differential of x squared plus 5 differential of x. Now, I've gotten to a dx term, so I know that there's nothing more that I can simplify here. But here I still am taking the differential of another function. So I have to continue one more step, and I use my power rule. Power rule says that the exponent will come down and become my new coefficient. So this is going to come down, and I'll reduce the exponent by 1. So power rule says that this is equal to 3 times 2x, and I still have to write dx, because that is what my power rule says. It says that if I've got a power, I bring the exponent down to be my coefficient, the exponent reduces by 1, and then whatever my base was, I still have to take the differential of it. That is one of the most common mistakes I see in first-year calculus students, is forgetting to hold on to their differentials. So that's there, and then we carry over the 5 dx. So now I can say that the differential of 3x squared plus 5x minus 4 is equal to 6x dx plus 5 dx. That's the differential. If I want to know the derivative, then I simply take the differential and I divide by the differential of x. So that's how I go from the differential to the derivative. And on the right-hand side, right, I've got dx is there, dx is there, dx is there, so they all cancel out. That way I know I did all my differentials right. So the derivative of this function is 6x plus 5. Or I can write using Newtonian notation that f prime of x is simply 6x plus 5. So let's take a look at another example. Let's say that f of t is equal to 3 minus t raised to the 4th power. So I need to take the differential of this function right there, right? I want to know what does f prime of t equal. So the differential of f is equal to the differential of 3 minus t to the 4th power. So again, as in the previous example, we need to investigate this and think about what is going on here. I've got some function here, and I could think of that as my u being raised to the 4th power. So if I can see that this is some function, name it u, to the 4th power, then really I've got the power rule going on here. And I'll have the differential of this term here. So this 4 is going to come down and become my coefficient, and this will reduce by 1. So I can write that as 4 times 3 minus t cubed. Now I can't forget my differential. So the differential moves through, doing its operation on the power rule, but I still need to take the differential of that inner function. Now, here I've got just the sum and difference rule, right? The d will distribute across addition and subtraction. So I get that this is equal to 4 times 3 minus t cubed, and then it's d3 minus dt. And d3 is 0, so this term is 0. And dt is as simplified as we can get. So now I've got this whole term times negative dt, so it ends up that this is equal to negative 4 3 minus t cubed dt. And my question is, what was f prime dt? Well, f prime of t we know is equal to df dt. And so I can take up here, just divide that by dt, and take this whole term and divide it by dt. And of course, that means that that dt and that t cancels, and this becomes negative 4 times 3 minus t cubed.